Perfect. So in the year 2000, they say that the population was approximately 6.04 million. And by 2050, it's projected to grow to 10 million. Okay. Use the exponential growth model. It's given to us. You don't have to memorize it. They're using K. Yes, they're using KT. Very good. In which T is the number of years after 2000. So when I'm told that T is the number of years after 2000, I will immediately write this note to myself. If T represents the number of years after 2000, T equals 0 must represent year 2000. So find an exponential growth function that models the data. And then in which year will the population be 9 million? So part A. So this is a function. What are the unknowns here? This is the unknown. This is a number. This is the variable in the function. It has to be unknown. But this is another defining characteristic. Once I have these two numbers, I know the function. So somehow I need to determine the initial population, and I need to determine K. Let me explain what K is. Growth rate. The growth rate. Exponential growth rate, if you want. What grows exponentially? I think I mentioned, I'll mention it again. People, bacteria, animals like birds or fish. Okay? Exponential growth. Okay. So can anyone tell us what is given to us? I'm told that in year 2000, 6.04, in year 2050, 10 million. So what does that mean? I'm basically given what? Here's my hint to you. But it's very important how I write it. So I am given two ordered pairs, but how do I write them? Can anyone give us an idea? How do we write these two ordered pairs? The year 2000 is 0, and the Y value is 6.04. What is 2050 in reference to 2000? How many years?
50.
Very good, awesome. And that's 10 million. These are our ordered pairs. Since we have two unknowns and we have two ordered pairs, these two ordered pairs, they will help us. The two ordered pairs will help us determine the initial population and the growth rate. So let's see how we do that. When I plug in 0 for T, I get the Y value 6.04. So this is 6.04 when T is 0. So A0, E to K times 0. Y is 6.04 when T is 0. So K times 0 is 0. How much is E raised to 0? 1. So then I found the initial population, which is 6.04. You can say, but you knew that from the beginning. True. I just wanted to prepare you for the next point. So for now, I do have that A of T equals 6.04 times E to K T. So I already determined the initial value, the initial number of people. Now I want to determine that, and I'm going to use the second point. Can anyone tell us how to plug in the second point, 50, 10, in what I have at this point? What do I replace this by?
10.
Excellent. Thank you. And this is 6.04 times E to K. What do I replace T by?
50.
Excellent. From here, we will be able to solve, after we solve this equation, when we solve the equation, we are going to have the answer for k. What is the first step here? Of course, it's an exponential equation. What will be the first step? And the answer is we have to clean it up. And we will be cleaning it up, dividing by 6.04. Final step, what should I do? What should we apply to both sides?
Log.
Excellent, thank you very much. Natural log to both sides. So the left-hand side is natural log of 10 over 6.04. The other side is 50k, because natural log e is 1. I should write times natural log e. There is no need, because this equals 1. So therefore, k equals all this divided by 50. Natural log 10 over 6.04 divided by 50. So I plug it in. Natural log 10 divided by 6.04, close the parenthesis please, and divide by 50. And it appears that the growth rate is, please use at least 4 decimal digits, 0.0101. If you want, you can use 5 or 6, but at least 4 decimal digits. So now we have the entire model. So it's 6.04 times e to 0.0101 t. We determine the model. Everything is known now. Part B of the problem is asking us to find in which year will the population be 9 million. So this was part A. In part B, population equals 9 million. How do we do that? Anyone? Starting point. I replace the population by 9. So then 9 equals 6.04 e to 0.0101 t. Everything is the same. Same equation, everything the same. This time I want to determine t. I will divide by 6.04. And of course apply natural log again. So natural log 9 over 6.04 equals, I bring this in front, 0.0101 t times natural log e, but that's 1. So t equals this over this. So natural log 9 divided by 6.04, and divide everything by, if you want, if you still have it there, just punch in previous answer and you will take the whole thing. And you will give us the best approximation possible. So 39.6. What does 39.6 mean? It's years since 2000. So it appears that in 2039, sometime, the population will reach 9 million. So this is this model. Now we want to discuss this one. Any questions on the exponential growth? And the last application, exponential decay. Any questions for me, please?
I don't have any questions.
Okay, thank you. Let's analyze something called half-life of a radioactive substance. And the example I like to give is aspirin. It's not a radioactive substance per se, but let's assume I take right now 100 milligrams of aspirin, and I'm just making this up. Oh, actually, there is a problem. I may not make it up. Problem 30 on page 530. The half-life of aspirin in your bloodstream is 12 hours. So what does half-life mean? So 12 hours. H, half-life, lowercase h, is 12 hours for aspirin. So if I take 100 milligrams right now of aspirin, 12 hours later, I have 50 milligrams in my bloodstream after 12 hours. Okay, after 12 more hours, I will have 25 milligrams in my bloodstream. After 12 more hours, I will have 12.5 milligrams in my bloodstream, and so on and so forth. This is the idea about the half-life. It disappears if you want. In 12 hours, half of it goes away. In 12 more hours, half of it goes away. 12 more hours, half of it disappears. That's the idea behind the half-life. So now let's work on this problem. The half-life of aspirin in the bloodstream is 12 hours. How long will it take for the aspirin to decay to 70% of the original amount? Okay. I know that it decays to 50% of the original amount in 12 hours. What I want to determine is how long it takes to decay to 70% of the original amount. So from 100% to 50%, it takes 12 hours. From 100% to 70%, it has to be less, because it takes 12 hours to go to 50. It will have to take less than 12 hours to get to 70. This is not the calculation. I'm just making sure we understand this. Because if the answer is more than 12 hours, we know something is wrong. Okay. So at this point, you will be given, the problem does not, but you will be given m mass of time t, at time t, mass, the original mass, times e to negative kt. Okay, so this is original, of course. Anything that has 0 as a suffix, it has to be original. Original mass. And this is the mass at time t. Mass at time t. Your book does not differentiate between amount and mass. They still use the same notation. I am fine with anything you want. It's the same thing. This is still the original mass, and this is still the mass at time t. It doesn't matter. If you want to use m, I use m to differentiate that it's not a number. It's a mass. This is a number, but it doesn't matter. It's the same. It's not a big deal. Okay, so knowing that, you want to use this or this, it doesn't matter to me. You want to stick with the same notation? We can stay with the same notation. Is that okay? But this time we're talking about mass, not a number. Anyone? Is this okay? Okay. So what I know so far is a point. I know that if I start at time t equals 0, at time t equals 0, I start with m0. Then at time 12 hours, what will m0 become? How much? 50% of m0. Excellent. Indeed, half of m0. Exactly. So if I take my medication, let's say my aspirin right now, I'm taking, let's say, 100 milligrams, but 12 hours later, I will have 50 milligrams. So 0, 100, and then 12, 50. But we don't have the original amount. This is not given to us. This was just an example to explain what the half-life means. This is what we have. Unknown amount that is original, but I know that 12 hours later, I will have half of it. So then from here, when I apply the point to the equation, then I have m0 equals, I just said that I was going to use a, so let me change to a. I just said that, but I'm in my mind, I'm still talking about mass, so that's why. Okay, so a0 equals a0 e to 0. Well, I don't have any new information here. It's just that a0 equals a0, but this is a preparation for this point. 12 hours later, the mass is a0 over 2 equals the a0, but now t is 12, e to negative 12t. What we really want to determine is what is t for 70% of a0. This is what we want to determine. So when time is t, when t is t, then the amount is 0.7 a0. 0.7 a0 equals a0 e to negative k t. I don't have a problem with this because I can divide both sides by it. But I have an unknown here. Before I find the decay rate, okay, in this case is decay rate. It's not a growth, it's a decay. It diminishes its mass. If I don't have the k, I cannot continue. So here, this is negative 12k. So t was 12 and negative k. So I have to go back and determine my k. So I can put it in here and determine t. So the left-hand side is 0.5. The right-hand side is e to negative 12k. I will apply natural log to both sides to get k. And then I'll come back to my equation. So I'm going to write it here. Natural log of 0.5 equals natural log of e to negative 12k. The left-hand side cannot be changed. I bring down negative 12k times natural log e, which is 1. So then I know that k equals natural log of 0.5 divided by negative 12. With k in place, so natural log 0.5 divided, don't forget to put parentheses around the denominator, negative 12. I got please use 4 digits at least, 0.0578. So then a of t equals a0 e to negative 0.0578t. And all I needed to do is continue here. So 0.7 equals E to negative 0.0578 T. And we will determine the time needed for the aspirin to decay to 70% of the original, whatever the original was. So we apply natural log. So natural log of 0.7 equals negative 0.0578 T. It should be multiplied by natural log E, but that's 1, and that's final. Natural log of 0.7, negative 0.0578, and then we approximate. It must be less than 12 hours. So natural log 0.7 divided by negative the previous answer. 6.17. 6.17 hours.